Okay, well, thank you, Christine. So the idea is, as you see, a 3D printer with error correction for atomically precise macro objects. What we want to do is leverage a couple of techniques. One is scan probe microscopy for atomic scale fabrication, but also some of the semiconductor industry techniques. The interferometry-driven servo stages for chip manufacture. You can actually process 10 chips per second with XYZ precision to 1.6 nanometer. That's one of the things we'll be utilizing. There's our team. So basically, what we want to do is create the atomically precise template once and then use it repeatedly. Okay? So let's look at how we might do that. So we're going to use an STM. I won't go through the details of that and how the patterning works, but here's a cartoon where we would take a surface, say a silicon surface that's atomically clean, just cartoon represented here. We'd come in with an STM tip and basically pluck out an atom. And there are publications where that's been done. And then what we do is repeat that process. So we would clear out an area, okay? And now we're going to switch to a simpler cartoon representation. And we might hydrogen passivate the surface. And then we would use selective chemistry to put the material that we want to transfer into that hole. So it would self-assemble into that hole with atomic precision. And then we'd come in with a stamp and transfer to that stamp. And then we could repeat that process. Okay, so here's the next layer. And now we transfer it to the stamp and so on. Now, you could have different shaped pieces that you're going to transfer. They're all atomically thin, so you would transfer them sequentially, and you could build objects that have, like a 3D printer, where each layer determines how the structure evolves. Okay. Another thing you could do is if you had a second material, a different type of material, then you could say, okay, I'm going to build that into the structure, and then you might be able to use that as a release layer. You might be able to subsequently remove it. So now what you've done is you've opened up the opportunity to make a NEMS type of actuator. So this would happen. So you'd have the scan probe that might be a millimeter away from where the transfer is going. So you could go back and forth between them because you're going to need to do some error correction. You're going to need to go there and verify, is the stamp still accurate? Do I need to put an atom back or take an atom out because of an error that's incurred during the processing? So we would use off-the-shelf technology in terms of UHV-STM, interferometry-driven servo stages. Like I said, the chip manufacturers can move a centimeter with 1.6 nanometer XYZ accuracy 10 times a second. And that's including the exposure step, so it's actually faster. So we envision if we're moving a millimeter, we might be able to do this whole process 100 times a second. The molecules or atoms that are going to be transferred would be introduced in the vapor phase. They would rapidly self-assemble into that little pit that we made in the surface. And then the stamp would come in and take it up. Lots of interesting things for AI control and error correction, as you can see here. Building the model, deposition process. It's a system. It's kind of like a self-driving car where you have to account for lots of things going on at the same time. So there's lots of image recognition, error corrections. So for example, we want to analyze the stamp to see if it's still atomically precise. If it's not, you have to fix it. Okay. What can you make with this thing? You could make new transistor technology like atomically precise FinFETs. If you use release layers, you could make objects that could be moved with atomic precision. Nano-electromechanical actuators for sensors, mechanical computing, or a radiation-hard computer would just have mechanical switches, for example. And small switches operating at 100 gigahertz are pretty interesting. Catalytic surfaces, you could design surfaces to taste for catalytic processes. You could make a porous type of structure that's mechanically strong but doesn't weigh much. Nano imprint templates, so you could make a print, you could print and make a template that can then be used to emboss very rapidly copies of itself. So that would be something also to consider. And actually, the one thing that's not on here is the semiconductor industry wants atomically precise templates so that they can actually calibrate their lithography systems. You could make that with this. Thank you.
Okay, we have 2 minutes for Q&A for this group. And